Okay, today we're in lesson 6.2, describing functions. Lesson 6.2, describing functions.
Okay, now let's take a look at some interesting bowling. Yeah, bowling is great fun. Have you ever bowled? Bowling is great. The only problem with bowling for me is that the ball is so heavy. If they ever got like wiffle ball going, I would be so into bowling with a wiffle ball. That'd be great. But until then, it's sort of a hard sport. Maybe it's hard for you. But in fact, let me actually do a shot right now. See if I can make it. So here we go. I'm just gonna do it right now. Here we go. Right now. In fact, I'll do it right now live. Here we go. Right now live. Here we go. There we go. It's off. It's going. It's going. It's going. Yes! You see that? That's called a strike, my friends. That is a strike. Okay, good. Well, in bowling, the equation h equals 160 minus 0.8s represents the handicap h calculated for a bowler with average score s. Okay, the question is, how much will the handicap be for each bowler listed on the table? And let's try to depict that with a graph that represents the relationship between the average score and the handicap. And then you can see all the names of the players and their average scores. And I want to now insert those values for s, those are s values, those are the average, in to try to find h. Okay, so here I actually started making the table for us. Let's take a look. These are all the s's. You can see 145, 125, 160, 140, 175. And then here's that formula for h. And all you can see that here I did was I just inserted for s that value. And I computed that number to be, in this case, 44. So I have the ordered pair 145, comma 44. I did that here as well. I just inserted for s the value 125, which is the s value here. And then computed that number to be 60, and then there's my ordered point. Here, for example, when I plug in 160, I get this thing, which turns out to be 32, and so my point is 160, comma 32. See? Here, for example, I'd see 160 minus 0.8, but now I'm multiplying it by 140. And so that would equal 48, and so I see the point 140, comma 48. And then finally, when I plug in 175 for s into this formula, see how I just did that? Then I see 20. This number works out to be 20. Now, I'm doing these calculations really, really fast, by the way. Of course, if we were doing them for real, it would take us a while to figure out that's 20, by the way. I don't think that you should just look at that and say, oh, it's 20. You have to do a little bit of work to see that's 20, but you can show that's 20. Now, let's take those points and see if we can plot them. So here are my axes. S and H, and now we're going to plot away. So 145, comma 44, that's right below 45. 125, comma 60, that's way up here. 160, comma 32, that's around here. 140, comma 48, that's a little below 50. Looks like it's sort of lining up. The points are lining up. 175, comma 20, right here. Well, what does the graph look like? It looks pretty linear to me. Does it look linear to you? Straight line seems to fit it perfectly. So, in fact, this is representing, in fact, a linear equation. And again, you can see that by taking a look at the fact, well, it's a little bit harder here, of course, because the x's here are sort of changing, well, in this case, the s's are changing sort of in a funny way. So it's difficult to actually see the reflections of the y's changing correspondingly. But the picture shows it to us very clearly. In fact, these points line up in a straight line. We see a perfect straight line. This, in fact, is an example of a linear function. Pretty cool. Anyway, wait a minute, the ball just came back. Remember how... That's the cool thing about bowling. Did you ever notice that? The ball always seems to come back magically. Anyway, it's pretty neat. So whether you're bowling out in the bowling lanes or whether you're actually thinking about mathematics or anywhere, it turns out that traveling in a straight line and being able to look at a function and see if it's linear is going to be really, really valuable. I'll see you straight ahead.
Okay, one additional thing you need to notice about this particular graph. Now, you can see that it's linear. It's a straight line. But notice how it's going through on the y-axis, how it's going through and it's not going through at 0. So whenever a line does not go through at 0 or has a y-intercept of 0, that's another way of saying that, we know the line is non-proportional. It's linear, but non-proportional. Once again, linear, but because it does not go through 0, it is non-proportional. If the line went through 0, we would say that it's linear and proportional. But once again, since the y-intercept is not 0, we say that it is linear and non-proportional.
So, a linear equation is just an equation whose graph actually can be represented by a straight line. So let's take a look at some equations and see if, in fact, they're linear or not. So what we're going to do, basically, is make a table of values for each equation, and then graph the x, y points in the plane, and see if, in fact, they line up in a straight line or not. Okay, so let's just get right to it. So here is the equation, y equals 2x minus 3. All right, now what do I want to do? Well, I'm going to just pick a whole bunch of x values, and for each of these x values, I'm going to insert them into the equation. I'm going to figure out the corresponding y value, and then I'll have an ordered pair. Remember, we always write x, y, and then I can export those points right to the plane. See what it looks like. All right, let's get right to it. So first, if I let x equal -1, and I plug it in here, I'll see 2 times -1 minus 3. And what does that work out to be? Well, that works out to be -5. And so therefore, I see the ordered pair -1, -5. Okay, now we can do it with 0. Plug in 0, I'd see 2 times 0 minus 3. That just yields -3. And so I see the point 0, -3. What about when I let x be 1? Then I have 2 times 1. You see, I always am plugging in the x value into its spot. -3. So that's going to be 2 minus 3 is -1. And so I see 1, -1. And notice I always write the x first, then y. All right, what about plugging in 2? I see 2 times 2 minus 3. So that's 4 minus 3 is 1. And so I see 2, 1. And then finally, my last point that I'm going to look at is 3. So I have 2 times 3 minus 3. So that's going to be 6 minus 3 is 3. And so I see 3, 3. Okay, let's plot away and see what happens. So here are our points. So -1, -5. -1 is right here. -5 is way down here. Put a point right there. 0, so 0 in the x direction, right on the y-axis. -3. 1, -1. These points look like they're lining up on a line or not? 2, 1. What do you think? 3, 3. Boy, they look like they're lining up on a line to me. If we connect them, wow, they line up perfectly on a line. This is linear. In fact, you can see it by looking at the table, by noticing something neat. Notice that the x's here are changing sort of at a constant rate. I just keep adding 1. I add 1 to -1, I get 0. I add 1 to 0, I get 1. 1 to 1, I get 2. 1 to 2, I get 3. And what's happening to the y values? Well, notice that they're actually changing at a constant rate too. Can you see what the constant rate is? Well, I have -5, and what do I have to add to it to get -3? Well, 2. And if I add 2 again, I get -1. And if I add 2 again, I get 1. And if I add 2 again, I get 3. So I can see this is linear because as the x's change constantly at a constant speed, a constant rate, then the changes in the y are also constant. That's our cue that we have something that's actually linear. Cool. Let's try another example. So this one is going to be the function y equals x squared. And the question is it linear? Okay, well, let's make up a table and see. So here we go, table time. So I picked -2, -1, 0, 1, and 2 for my x values. And now I'm going to just plug them in. So I'm going to look at -2 squared. Well, that's going to be 4. And so therefore, y is 4. And so I see -2, 4. When I plug in -1, I see -1 squared. And so that works out to be 1. And so I see the point -1, 1. When I plug in 0, I see 0 squared. That's 0. And so I see 0, 0. When I plug in 1, I see 1 squared. That's 1. So I see 1, 1. And finally, when I plug in 2, that's 2 squared, which is 4. And so I see 2, 4. So now I have a table of coordinates that I can now plot. -2, 4. -1, 1. Looks like it could be a straight line. It's looking good. 0, 0. Well, that's sort of there's a little kink to it, but maybe that's just because I drew it wrong or something. Let's see. 1, 1. Whoa, 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 whoa. There is no way this is going to be linear. 2, 4. This does not look like a straight line at all. In fact, this looks like a really not straight line looking thing. It's actually an example of what's called a parabola. And that is absolutely not a straight line. And we can see that, by the way, because notice that the x's, there's constant change in the x, right? I'm increasing by 1 each time. But the y's are not changing at a constant rate. To go from here to here, I have to subtract 3. And then to go from here to here, I have to now subtract 1. That immediately tells me this is not linear, because as the x's change at a constant rate, the y should change at a constant rate as well. So is it linear? Absolutely not at all. How about this one? Here's one. Let's try this. Y equals 2x divided by 3. Okay, is it linear or not? Let's make a table and take a look. Okay, so when I plug in negative 2, I see 2 times negative 2 over 3. That's going to be negative 4/3. So I get the point negative 2 comma negative 4/3. Plug in a negative 1. I see 2 times negative 1 over 3, which is going to be negative 2/3. So I see negative 1 comma negative 2/3. Lots of fractions here, but that's okay. Plug in 0. 2 times 0 divided by 3 is 0, so I see 0, 0. When I plug in 1, I see 2 times 1 over 3, which is just 2/3. So I see 1 comma 2/3. When I plug in 2, I see 2 times 2, that's 4 over 3, so that's 4/3. So I see 2 comma 4/3. And finally, when I plug in 3, that's 2 times 3 over 3. There's a little simplification, 3 over 3, that just simplifies to 2. And so I see 3 comma 2. All right, let's plot the points and see what happens. Here's my plotting the pen point. There we go. Whew. All right, now lots of fractions here, so we got to be really careful with our picture. Negative 2. Negative 4/3, so that's down to negative 1. And then I have to go down another third, so that's right here. Negative 1, that's right, it's negative 2, negative 4/3. Negative 1, negative 2/3, that's not quite down to negative 1. 0, 0, that's an easy point, I can put that in. 1, 2/3, so 1 and I go up 2/3. That's 1 right there, and that's a little below it. And then 2 4/3, that's 1 1/3. And then finally 3, 2. That's an easy point. Do they look like they're lining up? They sure do. This is linear. Perfect straight line. And again, you can see that because the x's are changing at a constant rate. And you'll notice that the y's, in fact, are changing at a constant rate as well. To get from here to here, I add 2/3. 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 So that shows that it's linear. How about this one? Y equals negative 3. Let's just zip through this one. This is going to be a real fun one. Because there's no place to insert x's, notice. So therefore, when it says x equals negative 2, well, negative 3 is still negative 3. So y is negative 3. This point is negative 2, negative 3. When x equals negative 1, there's no place to put the x, so it's just negative 3, negative 3, negative 1, negative 3. These are negative 3's right down the whoop. You see, because it's just negative 3. It doesn't depend upon x at all. So the y's are always negative 3. So 0, negative 3, 1, negative 3, 2, negative 3, 3, negative 3. Okay, now let's plot points and see where we are. Negative 2, comma, negative 3, right here. Negative 1, negative 3. 0, negative 3. 1, negative 3. 2, negative 3. 3, negative 3. Boy, they are absolutely on a line. In fact, you can see the line. It's a horizontal line. And again, you can see that by looking at the graph, by the table here, because we see that the x's are changing at a constant rate of 1 unit each time, and the y's are changing at a constant rate. Can you see what the constant rate is? 0. I take negative 3 and add 0, I get negative 3. Add 0, I get negative 3. Add 0, I get negative 3, negative 3, negative 3. So 0 is the constant rate. That counts. That's it. It's a line. Absolutely cool. So you can actually tell whether you've got something that's linear or not by producing a table, seeing if the y's are changing at constant